Hello, my name is Margaret. Today we're going to talk about combining functions. Let's look at our objectives. First, we'll look at arithmetic operations on functions, and then we'll look at composition of functions. Now we can add, subtract, multiply, and divide functions just as we can numbers. Let's look at the definitions for these operations. If f of x and g of x both exist, the sum, difference, product, and quotient of two functions, f and g, are defined by f plus g of x equals f of x plus g of x, f minus g of x equals f of x minus g of x, f times g of x equals f of x times g of x, and f divided by g of x equals f of x divided by g of x, where g of x does not equal 0. Now, whenever we talk about functions, we have to be careful about domains, and that's especially true here. The domains of the sum, difference, and product of f and g include x values that are both in the domain of f and the domain of g. The domain of the quotient f divided by g includes all x values in both the domain of f and the domain of g, where g of x does not equal 0. Let's look at two functions, and we'll find domains and combine our functions. Let f of x equal 3 minus the square root of x minus 2, and g of x equal 2 minus x squared. We want to find the domains of f of x, g of x, f plus g of x, f minus g of x, f times g of x, and f divided by g of x. And then we'll write expressions for f plus g of x, f minus g of x, f times g of x, and f divided by g of x. First, let's find our domains. Now, our domain of f here, it consists of all real numbers as long as x is greater than or equal to 2. So our domain here is the set of all x such that x is greater than or equal to 2. For g, this is a polynomial function. In fact, it's a quadratic function. The domain is all real numbers. Oops. Now, for f plus g, the domain of f plus g must consist of all numbers that are in the domains of both f and g. That means the domain is the set of all x such that x is greater than or equal to 2. F minus g, the domain is the same, the set of all x such that x is greater than or equal to 2. F times g, the domain is the set of all x such that x is greater than or equal to 2. F divided by g, now we have to be careful. Remember that it has to consist of all the numbers that are in both domains for f and g, so that would be all real numbers x greater than or equal to 2. But we cannot have any values of x which make g of x 0. So let's see if we can find the values that make g of x 0. We find in this case that x squared equals 2, or x equals plus or minus the square root of 2. Now, both of these numbers are less than 2. So the domain for our function f divided by g will consist of all real numbers x, such that x is greater than or equal to 2. Now we've checked the domains. Now we're ready to find these new functions. The first one we want to find is f plus g of x. So that says we simply add f of x plus g of x. And let's remember to collect like terms. 3 plus 2 is 5, minus the square root of x minus 2, minus x squared. F minus g of x, we have 3 minus the square root of x minus 2, minus the quantity 2 minus x squared. Now it's especially important here that you put these parentheses. We'll have to remove our parentheses and then combine like terms. So we have 3 minus 2 is 1, minus the square root of x minus 2, plus x squared. F times g of x, we have 3 minus the square root of x minus 2 times 2 minus x squared. And f divided by g of x, we have a quotient with 3 minus the square root of x minus 2 in the numerator over 2 minus x squared. Let's take a look at an application which uses a combination of functions. Methane is a greenhouse gas. It lets sunlight into the atmosphere, but blocks heat from escaping the Earth's atmosphere. Methane is a byproduct of burning fossil fuels. In the table, F models the predicted methane emissions in millions of tons produced by developed countries. The function G models the same emissions for developing countries. Here's our table. Now remember, F is the amount of emissions for developed countries and G of x for developing countries. X is the years. Now, the first thing we want to do is to make a table for a function h that models the total predicted methane emissions for developed and developing countries. Here's our table. We want to add the two together to get the total emissions for the developed and developing countries. So we'll simply fill in our table by adding the numbers in each column. Now, we'd like to write an equation that relates f of x, the amount of emissions for developed countries, g of x, the amount of emissions for developing countries, and h of x, the total amount of emissions. Well, since we added those together in our table, it makes sense that we simply add the functions. So the new function we've created, h of x, is equal to f of x plus g of x. Now, there's another way we can create a new function, and this new function is called a composition of functions. Here's our definition. If f and g are functions, then the composite function g composed with f, g composed, this is a little circle, it's like a degree symbol, but it's midway up the line, not as high as a degree symbol. G composed with f, or the composition of g and f, is defined by g composed with f of x equals g of f of x. The domain of g composed with f is all x in the domain of f such that f of x is in the domain of g. Let's look at this example. We'd like to find a symbolic representation for the composite function g composed with f that converts x miles to inches. Now think about converting miles to inches. We might first convert miles to feet. Suppose we let f of x equal 5,280x, where x is the number of miles. And we do this because we know there are 5,280 feet in a mile. Now, if we have a number in feet, we can convert that to inches by multiplying by 12. So let's write g of x equals 12x, converting an input, which is in feet, by 12 to give us the number of inches. G composed with f of x would be g evaluated at f of x. So this is g evaluated at 5,280x. So this would be 12 times 5,280x, which is equal to 63,360x. So our composite function g composed with f of x is equal to 63,360x, and this converts our x miles into inches. Now please be careful here. There is a great difference between multiplying two functions and finding a composite of those two functions. Let's just review this to make sure we know the difference. With the product, f times g of x equals f of x times g of x, both f and g receive the same input x. Then their outputs are multiplied. However, with the composition f composed with g of x equals f of g of x, the output g of x provides the input for f of x. Let's look at an example where we will evaluate a composite function and then actually find an expression for a composite function. Let f of x equal 2x squared minus x and g of x equal 1 over x minus 1. First, we'd like to evaluate f composed with g of 2 and g composed with f of 2. So f composed with g of 2 is equal to f of g of 2. Now that means I have to evaluate g when x is 2. So I have 1 over 2 minus 1, which is 1 over 1, or 1. Now I will evaluate f at 1. So I'll substitute 1 for x in the expression for f. So I have 2 times 1 squared minus 1, which gives us 1. So f composed with g of 2 is equal to 1. Now, let's do the composition in the other order. G composed with f of x, f of 2, is equal to g of f of 2. Here, we have to evaluate f at 2. So 2 times 2 squared minus 2 is 8 minus 2, or 6. So we now have to evaluate the function g at 6. G of 6 is equal to 1 over 6 minus 1, or 1/5. Now, did you notice that the two numbers, or the two answers rather, are different? That's important to remember. The composition of g with f is not always equal to the composition of f with g, all right? So they may not be the same. Now, we're ready to finish our problem. We want to find symbolic expressions for both of our compositions. First, let's look at f composed with g of x. So that's f of g of x. All right. So this says we have to look at f evaluated at 1 over x minus 1. So wherever we have x, we have to put 1 over x minus 1. So we have 2 times 1 over x minus 1 squared minus 1 over x minus 1. Now this gives us 2 times 1 over x minus 1 squared minus 1 over x minus 1. Now, in order to combine these, we have to find our common denominator, which is x minus 1 squared. So we have f of g of x is equal to 2 over x minus 1 squared minus 1 over x minus 1. Now remember, we're going to have to multiply this second term by x minus 1 over x minus 1. So we have 2 minus the quantity x minus 1 over x minus 1 squared. Now we have to remove our grouping symbols. 2 minus x plus 1 over x minus 1 squared. And this gives us 3 minus x over x minus 1, the quantity squared. Now we have to do the composition in the other order. We want to look at g composed with f. So g composed with f of x is equal to g at f of x. So here we have g evaluated at 2x squared minus x. Now g, remember, is 1 over, in this case, this is what we're putting in for x in the function rule for g, so that's 2x squared minus x minus 1. Now, one thing we should do here is to check the domains for both of our composite functions. Now, the domain of f is the set of all real numbers. The domain of g is the set of all real numbers except x equals 1. So we know the domain of the composite function cannot contain x equals 1. Now, let's take a look at our composite functions again. F composed with g of x, remember, is 3 minus x over x minus 1, the quantity squared. In this case, the only problem area we have was when x is equal to 1. So the domain here for f composed with g is that x is a member of the set such that x, of all real numbers, such that x does not equal 1. Now, for g composed with f, it's a little more complicated. Remember that g composed with f of x is equal to 1 over 2x squared minus x minus 1. This denominator cannot be 0. So let's find out if it is 0, and if so, where? Well, this is quadratic. It looks like it factors. So let's try. We'll put 2x and x, 1 and 1. Let's put our plus sign here and our minus sign there. And check your outer and inner products again. So 2x plus 1 equals 0, or x equals negative 1/2. And x minus 1 equals 0. So x equals 1. So the two values we have to exclude from the domain are x equals negative 1/2 and x is equal to 1. So the domain for g composed with f then consists of the set of all x such that x does not equal negative 1/2 and x does not equal 1. Here's another example. Let f of x equal x, the absolute value of x minus 1, and g of x equal x squared. Find f composed with g at negative 3. Find a symbolic representation for f composed with g of x, and find the domain of f composed with g of x. Now, I would like you to stop the tape here and try this problem yourself. Well, let's see how you did. Our first task is to find f composed with g of negative 3. So we have f composed with g of negative 3, so this is f evaluated at g of negative 3. Well, let's find g of negative 3. Substituting negative 3 for x and squaring, we find that g of negative 3 is 9. Now we can evaluate the function f when x is equal to 9. So that would be the absolute value of 9 minus 1, or the absolute value of 8. Next, we'd like to find a symbolic representation for our composite function. F composed with g of x is f at g of x. Now remember that g of x here was x squared, and f was the absolute value of the input, in this case x squared, minus 1. So this is the symbolic representation for our composite function. Then we wanted to find the domain of our composite function. Now, remember that f of x was the absolute value of x minus 1. G of x was equal to x squared. And both of those exist for all real numbers. So the domain for the composite function, which was the absolute value of x squared minus 1, would also be all real numbers. So we'll write the domain for f composed with g is the set of all real numbers. Now, it might be interesting to take a look at the graph of this composite function. Let's enter our two functions in our calculator. So we have y equals the absolute value. So we go under math, find our absolute value of x minus 1. And let's let y2 equal our g of x, which was x squared. And I'm going to put this in a window that goes from negative 5 to 5 on both axes. So there's our absolute value function. And there's our quadratic function, g of x. Notice that both of them have domains which are sets of all real numbers. Now, to graph the composite function, let's go back to our y equals menu and turn off our two functions. And come down, and in y3, we want to remember evaluate our absolute value function at x squared. So we'll go to our vars menu and our y vars, and go to our y vars, there we go, go to function, and pick off our first function, y1. Now we're going to evaluate that, so let's use our parentheses, at y2. So we'll go to vars again, y vars, function, and now we'll pick off 2, y2, and close our parentheses. Now let's graph that function. And this gives us our composite function, the graph of our composite function. Well, today we looked at combining functions by our arithmetic operations, addition, subtraction, multiplication, and division, but also with this new way of combining functions by using composition. Make sure you do all the homework your instructor assigns so that you become very proficient with these kinds of tasks. Have a good day.